Section 5.3 is all about substitution, and substitution is actually a really powerful tool in terms of integration. With substitution, it gives us a way to work through problems that have like a product or a quotient rule. So unlike differentiation, which had the product and quotient rule, integration's not quite that nice. It's a little bit harder to break up our stuff. So the fundamental theorem of calculus gave us a method to evaluate integrals without using Riemann sums, which is wonderful. We love that. The drawback of this method, though, is that we must be able to find an antiderivative, and this is not always easy. In this section, we examine a technique called integration by substitution to help us find antiderivatives or integrals. Specifically, this method helps us find antiderivatives when the integrand is the result of a chain rule derivative. At first, the approach to the substitution procedure may not appear very obvious. However, it is primarily a visual task. That is, the integrand shows you what to do. It is a matter of recognizing the form of the function. So what are we supposed to see? We're looking for the integrand of the form f of g of x, g prime of x dx. So they do this example here. Basically, guys, when we're doing this, we're looking at compositions of functions. So like f of g of x. And what our goal is to try to figure out, okay, what represents that g of x? What's the inner part of that composition? Now, this is not always the case, but for most everything that we're going to be doing, this is the case. It's always that composition that we're trying to peel apart. So here in this particular example, you do have the composition of x squared minus 3 cubed. Now, you do have this 2x. That 2x is actually a fallout from the chain rule. So with this composition, my g of x would be the x squared minus 3, and that's what becomes my u. So the method is called substitution because we substitute part of the integrand with the variable u and part of the integrand with du. So it is also referred to as change of variables because we're changing variables to obtain an expression that is easier to work with for applying the integration rule. So we've got theorem 5.7 here that tells us how to do substitution with indefinite integrals. Now, we do have two different substitution rules, one with indefinite, one with definite. They're almost the same thing, except for with the definite, sometimes we have to change our bounds. So let u be equal to g of x, or whatever that inside function is, where g prime of x is continuous over an interval. Let f of x be continuous over the corresponding range of g, and let big F, which is the antiderivative of f of x, little f of x. Then the integral of f of g of x, g prime of x dx, is really the integral of f of u. And then we can integrate, get the original function of u, and then replace u back with that x value. And of course, because it's an indefinite integral, we have to do plus c. All right, so here's a proof of that information. I'm going to leave that for you to kind of glance over. Next thing I want to look at is this idea of the problem-solving strategy. So to do integration by substitution, you look carefully at the integrand and select an expression g of x within the integrand to set equal to u. So let's select g of x such that g prime of x is also part of the integrand. And then you're going to substitute u equals g of x and du equals g prime of x dx into the integral. Now, this part where it says where g prime of x is also part of the integral or the integrand, sometimes it's almost like it's in a hidden form. So sometimes when you go to take a derivative, you've got more than what's actually showing in the integrand, so you have to account for that. We should now be able to evaluate the integral with respect to u. If the integral can't be evaluated, we need to go back and select a different expression to use as u. You evaluate the integral in terms of u and then write the results in terms of x in the expression g of x. Now, we're not going to get to it, but not every integral can be worked this way. They do have some rules that we don't get to look at. I'm not gonna go over them. But there are some rules that kind of go with this to make finding the integral a little bit easier that they've proven. Guys, also be aware with the trigonometric functions. Sometimes with trigonometric functions, you get kind of caught in a loop. And now it's not going to be so much in this particular section. Ours work out pretty nicely. But if you do decide to go on and take Calc 2, sometimes you get caught in this loop and you have to find a way to kind of go around that. All right, let's do an example here. So we are going to do number 261. So in the following exercises, find the antiderivative using the indicated substitution. So these first couple of problems that I'm going to do are really nice because they go ahead and they tell us what u is supposed to be. And then they're going to take this little crutch away from us and say, here, you figure it out. So in 261, we have the integral of x plus 1 raised to the 4th dx. And they're going to tell us that u equals x plus 1. Now, if I was doing this problem, I would have picked u to be equal to x plus 1 because that's what's on the inside of that composition. So that would be my g of x. So let me pull up a whiteboard here. And I'm going to have dx, and we also know that u equals x plus 1. So here's what I'm going to do. And this, you're going to see me do the same exact thing when we have to pick our u. So after I pick my u, you're going to see me go through, and I'm actually going to solve this thing for du, or excuse me, dx. So, but I have to find du dx. So I'm going to take the derivative of this. So du dx is equal to 1. So this one's really nice. And then of course I go through and I take the integral over here, excuse me, I replace my integrand with the u. So whatever I was making my substitution. So now I'm going to have the integral. Why aren't you writing? The integral of u to the 4th. And then I'm going to rewrite my dx to be du dx. Now, what I normally would do though is I would normally change once I did my derivative over here where I've got the du dx equals 1, I would go ahead and solve that for dx. Now I know it sounds weird, but we're going to solve this thing for dx. And if I do that, I'd multiply both sides by dx. So I'd have du equals dx. And that's why instead of writing du dx, I can just replace that with du, which is what we're after. All right. So now, as I go through and take my integral, notice taking the integral of u to the 4th is much easier than trying to figure out what the integral to x plus 1 raised to the 4th is. So the integral of u to the 4th is going to be 1/5 u to the 5th plus c. And then, of course, I'm now going to replace that u with what my substitution was. So u is actually x plus 1 to the 5th plus c. So that one's not too bad. They do get tricky. I found this section as I kept working through it, and it may have just been the time of night that I was working through it. I got so frustrated with some of the math because with these, if you mess up a sign or you skip just the smallest detail, the whole entire thing is wrong. And it is so hard to figure out what you've done wrong to get these things right. So you want to make sure as you're working through these that you are taking your time and making sure you're watching your math very closely. And that's going to save you a lot of headache. All right. So now I'm going to clear this out. We're going to do number 265. So same idea. So on 265, they give me the integral of x over the square root of x squared plus 1 dx. Now I'm trying to get us in the habit of figuring out what our u is going to be as we go. Now they do give me my u, but let's talk our way through this. So on this one, notice my composition actually occurs in that square root of x squared plus 1. That's where I've got the composition. So my u, I'm going to make x squared plus 1. So what's underneath that square root? And that's actually the u that they give us in the book. It's x squared plus 1. So I'm going to go ahead and I'm going to solve I'm going to go ahead and take the derivative of my u. So my u is actually going to be du dx equals, because I'm taking the derivative with respect to x. This would be with derivative with respect to x, this is going to be a 2x. And the plus 1 goes to 0. Now, do you see how you've got this dx here? You want to be able to replace dx with du. So I need to solve for dx, which is what I did in the last problem. It's just the last one was really nice because you got 1. So here, I'm going to multiply both sides by dx. If I do that, I now have this statement du equals, these cancel out here, du equals 2x dx. Still solving for dx, I'm going to divide both sides by 2x. So really du over 2x equals dx. And I know it looks really weird and you're like, why on earth would I do that? You're going to see why we do that. Hopefully, if I've done this correctly, I'm going to have some things cancel out. So let's go through, and I actually want to rewrite my integral. So I'm going to use this piece here in a moment. I'm going to use this piece. So that's the 2 pieces I needed out of that. So if I rewrite my integral here, my integral is actually going to be x times x squared plus 1 raised to the negative 1/2 dx. So that's what my integral is currently. Remember, we don't like having that division and the square root and all that on the bottom. So I'm going to pull it up on top using my exponential rules. And now I'm going to replace my stuff with u's and du's. So I don't have a replacement for x. So the x is going to stay. But this x squared plus 1 in parentheses is now going to be u to the negative 1/2. And my dx is going to be replaced with du over 2x. Now, watch how cool this is. If you've done this correctly, everything that's going to be an issue should cancel out. So notice in this problem, I've got x's and u's. And we just want to have u's. That's what we're after, is just u's. But because of this piece here, this is actually going to allow me to cancel out the x, right? Because you got an x on top and an x on bottom. So now you've got that du over 2. Du over 2 is really equivalent to saying 1/2. So I can actually pull that 1/2 out to make it a little bit easier using the rules of integrals. And if I pull 1/2 out, I'm going to have 1/2 the integral of u to the negative 1/2 du. So now I'm going to go through and I'm going to take the integral. The integral is going to end up being, remember that we take our exponent, add 1 to it. So negative 1/2 plus 1 is going to be u to the 1/2. And you divide by your new exponent, which is 1/2. And then, of course, we've got du. Or, excuse me, du, the integral of du is just, it cancels itself out. So we've got plus c. Let me rewrite this to where it's a little bit prettier. If you've got divided by 1/2 on the bottom, that's actually going to multiply by the reciprocal. So you're multiplying by 2. So you've got 1/2 to u to the 1/2. So the 1/2s cancel out. So really, you've just got u to the 1/2 plus c. And now I'm going to switch out my u to be x squared plus 1. So this is x squared plus 1 to the 1/2. Or if you want to get real fancy with it, this is actually the square root of x squared plus 1 plus c. Remember, with indefinite integrals, as long as they don't give me an initial a value there, we're always going to have the plus c. Let's do a sine cosine one. So let's throw some trig up in here. So I'm going to do number 269. So 269, we have the integral of cosine cubed theta, and then we've got d theta. Now let me make sure they've not changed directions on me. 269. Nope, we're still given our u. So in this case, our u is going to be sine theta, is what they're telling me. Let me look at it again. 269. Yeah, 269 u is equal to sine theta. And you're like, okay, that's great. We don't have sine theta. So here's what happens with trig again. And I mentioned how trig you have to be careful with the trig ones because they loop. And so sometimes it feels like you're in a never ending loop that you can't get out of. With trig, a lot of times you see yourself using your trig identity. So I'm going to go back to trig class. And what I'm going to do is I'm going to try to get a sine out of this cosine cubed. So if I try to get a sine out of cosine cubed, I could rewrite this to be cosine cubed. I could rewrite it to be cosine squared theta times cosine theta d theta. And I know you're thinking, well, that's still cosines. But I can rewrite cosine squared to be this. And I'm actually going to put my cosine theta up front just because I want to. 1 minus sine squared theta. Because we know cosine squared is equal to 1 minus sine squared theta. And guys, one of the reasons that I need to do this, because you're probably looking at this like, well, didn't we just make this problem way more complicated than it needed to be? When you take the derivative or you take the integral of cosine, you know you're going to go to sine. So I need to incorporate sine in here because if I don't, I'm just going to have a bunch of sines that I'm not getting rid of the d theta. So that's why instead of using like cosine, we have to go back to sine. So this is an example of where you don't actually use the function that you would think you'd be using until I get over here and I see that cosine squared is 1 minus sine squared. And now I know what you're also thinking. You're like, well, why didn't we use 1 minus sine squared? The book told us on this one to use sine theta. So one of the things I want to make sure that I do right quick is I'm going to go ahead and change sine theta, or I'm going to take the derivative of both sides of this with respect to theta. So I'm going to have du d theta equals the derivative of sine theta is cosine theta. And now I need to solve this for d theta because I want to be able to replace this d theta. So if I solve that for d theta, I multiply both sides by d theta, and then I'm going to divide by cosine of theta. So I'm going to have du over cosine theta equals d theta. So I need this piece and I need this piece to be able to do this. So now I'm going to go back and I'm going to rewrite this to be, or my integral to be, the integral of cosine theta times 1 minus sine squared. Remember, sine is u, so I'm actually going to have u squared. And then d theta, I'm going to replace with du over cosine of theta. Now, this is another reason why they chose u to be sine. You see how when I took the derivative, I've got that cosine theta. You see this cosine theta here and this cosine theta here. Those two things are actually going to cancel. Guys, if you've still got a product in here when you're trying to integrate, you kind of got an issue. Unless you can do it by the power rule, we don't have a product rule for integrals. So you always want to make sure you're kind of working in the format of power rules. So now I've got the integral of 1 minus u squared du. And that's pretty easy to take the integral of. The integral of 1 is going to be u because you add, that's really the same thing as saying 1u to the 0. We add 1 to it, so we've got u minus, you can write it u cubed over 3, or I'll write it that way this time. Typically, I like to write it minus 1/3 u cubed. That's just personal preference. It's completely up to you. This way actually follows the rule a little bit more. And then plus c. So now I'm going to plug in with what u was. So now u is going to be sine theta minus 1/3 sine cubed theta, or you could write sine cubed theta over 3, same thing, and then plus c. Now, what's so awesome about this, you know, besides the plus c, is you can actually check your answer. If you go back through and you take the derivative of sine theta minus 1/3 sine cubed theta, you will get back to cosine cubed theta. So that's pretty nice. Okay. So now I want to look at some problems where we actually have to pick our U's. So I'm going to jump to 275. Or you know what? I'm going to start a new video. Let's do that. So I'll start a new video. I'll see you guys in just a moment.